Today's notes is called linear programming, which are applications of linear inequalities. So we're going to go over how systems of linear inequalities are used in the real world. So there's some words that are going to be popping up and could be in some of your questions that are on your assignments or on your upcoming performance task. So just kind of want to go over those. The first one is, what is linear programming? So a linear programming is a method for maximizing or minimizing a linear function depending on certain constraints. You're going to see something called the objective function, and that is a linear function that you're going to write, which can be used to either maximize or minimize certain things. So we're going to be talking about real world with money, so things about cost, revenue, and profit. And so we're going to be focusing on profit today and cost. So you're going to see questions related to what is the cost function? What is the profit function? So when they ask you to find that, that means they want you to write a linear function using information from the word problem. Constraints are linear relationships that restrict the objective function. And the feasible region is that shaded area that we've been practicing that contains all the possible solutions to a system of equations. So because we are doing real world scenarios, we're going to have to go over certain keywords that were from the old days, from middle school to Algebra 1, when you were doing word problems for the first time with inequalities. So there's certain words that tell you to use like a greater than symbol versus a greater than or equal to, a less than or less than or equal to. So these are some examples. It's not every possibility, but they're the most popular ones. So you can use that as a reference. There are going to be equations that use larger than normal values, especially when we're talking about money in the real world. It's not all going to fit on a -10 to 10 scale. And so to graph these inequalities, we're going to use a graphing method. It's called the intercept method, where we don't convert mx plus b, and we're not going to start with the y-intercept, and we're not going to use rise over run. Instead, we're going to graph the x-intercept and the y-intercept and then connect that to make our linear. So example 1 says, Miss Daniels has a maximum of 100 ceramic goods available for the HHS Floral Club to decorate monthly bouquets. She has at least 40 vases in her storage room. She also has a minimum of 10 baskets that can be used. So just for practicing the intercept method, we went ahead and wrote out what those pieces of information are. So there are two topics or two items that are being utilized. We're going to use X to represent the number of vases and Y to represent the number of baskets. We wrote 3 inequalities from the information given in that word problem. So for example, when it says she has a maximum of 100 of those ceramic goods, that means together the vases and the baskets. So you can see that X plus Y there to represent that together. And since it's a maximum, we can see like in our list here that maximum means less than or equal to. Since you can't have more, you can only have less, but you could be equal to that 100. She also has at least 40 vases. And so since vases is X, you can see that X inequality. At least, when you look at our list, it's here with that greater than or equal to. Since you can have the word at, that means you can equal 40. And since 40 is the least, then you have to go bigger, and so you want a greater than. And then the last inequality comes from a minimum of 10 baskets. And so again, minimum is on our keywords here. You can have that 10 as your minimum, so you have the equal to. And since 10 is your min, then you can only go bigger, so same thing, a greater than or equal to. All right, so we're going to graph these inequalities. So 2 of them are super easy. They're already in those Hooy-Vux forms that we've been practicing. So our second inequality here, that x greater than and equal to 40, that is going to be a Vux, a vertical line at 40. So let's find our x at 40. we're going to do a vertical line, and because it's equal to, we're going to keep it solid. Let me draw that just a little bit better. And then we'll do like how we did last time. Let's make that a little bit thicker. How we did last time, and we're going to draw the arrows and then shade in that final area. So because we are greater than or equal to, we will eventually be shading towards the right of that vertical line. Okay, our last inequality is a horizontal line where y is 10. So let's go to our y-axis at 10. It is an equal to, so let's do a solid horizontal. And then it is a greater than, so we will be shading above eventually. And then we got one more, and then we'll find that final shaded area. So our top equation, x plus y is less than or equal to 100. If you really want to try, you're welcome to convert that to an mx plus b, and then you can count with your slope. But eventually your slope is going to become a 1, and so since our graph is not counting by 1, it's not always the best, but it is possible. Instead, we're going to show you that intercept method. So I went ahead and set up that same inequality twice because we're going to do round 1 for the x-intercept and round 2 for the y-intercept. So let's say I do the x-intercept first, and it doesn't matter which one that you do first. We need to remember that an x-intercept is when you can solve for an x value when the y value is automatically 0. So to do that, we're going to sub in 0 for y, and then we're going to solve for x. And instead of keeping it as an equal sign, or sorry, less than or equal to, we're going to temporarily change it to an equals. Not that we're taking away from the inequality, but right now we're just solving for one value. I just want to know that one value that x is going to be when the y is 0. And so when we solve for x, that x would end up equaling 100. So that means we have an x-intercept at 100 and 0. So let's go ahead and go to our x-axis and plot our x-intercept at 100, 0. We'll do the same thing, but this time with a y-intercept. And remember, a y-intercept is opposite. Our 0 is on the x spot, and our y is whatever value you get when x is equal to 0. So this time we're going to substitute 0 into the x spot. Again, temporarily solving for our y-intercept. So we're going to temporarily set it up as an equal sign. And then we can see that y is also 100. They're not always going to match, especially when you have other coefficients. So just make sure that you do your due diligence and actually do the solving. So we have a y-intercept out of 100. So now all we have to do is use a ruler or a sharp edge, the edge of your calculator, to graph that last inequality. I'll make it a little bit thicker just for the video's sake so you can see a little bit better on your screen. And then going back to what that inequality was, that was a less than or equal to. So we are going to shade below. And then the area where our colors mix, that will be our final shaded region, which they are calling your feasible region. All possible values that will make all three of those true. So we have done that step in the past, just not so much with word problems. And so now we're just adding in that next layer, and then how we use the shaded region to help us determine whatever profit or whatever our goal is going to be. So we're going to practice that on round 2. Went ahead and copied and pasted those keywords for you as you do this problem. So example 2 says the HHS Sports Booster Club is selling new Hawks volleyball hoodies and shirts. They have a maximum of 200 items available for sale. The HSB, short for the Hayes High School Sports Booster Club, expects to sell at least 30 hoodies at the next game night. They also plan to sell at least 10 shirts. If the HSB sells hoodies for $25 and shirts for $15, what combination of hoodies and shirts need to be sold to maximize their profit? So that's our end goal. How do we determine which of those numbers is going to maximize our profit? So we're going to kind of go over the steps like we had practice with our systems of equations word problems. But now we're going to do it as a system of inequalities. So first thing is identify our variables. What are those two topics that are happening in this problem? So because our sports booster is selling hoodies and shirts, those are going to be our variables. And it does not matter which one that you pick, just make sure that you're consistent with it. So I'm just going to go with whatever I see first. So I see hoodies first. Hoodies will be my X, and then that makes shirts my Y. And I'm just going to remind myself that later on when we actually start to answer our end goal question is how many of each do we actually need to make the most money? All right, so now we're going to read and we're going to write our system of inequalities. So let's see what we've got in our story. It says they have a maximum of 200 items available. So those 200 items include both the hoodies and the shirts. So together, we're going to represent that as an X plus a Y. And we have a maximum of 200. So maximum means that's the most that we have. So we can't get any bigger. That means we're going to have to go smaller. That's a less than. Now, we do have 200 items, so that means we could sell all of those 200 items. So we are going to do n equal to. And then you can also see that maximum is listed here with that less than or equal to symbol. The HSB expects to sell at least 30 hoodies, so that's our next piece of information. We're going to say at least 30 hoodies. All right, so for hoodies, we said that we are using the X. And I know I have at least 30 hoodies, so 30 is going to be in my inequality. The word at means we're going to underline. And if 30 is the least I can sell, then I need to sell more than that. So I want a greater than. And again, you can see that in your list for your refreshers on those word phrases. Now, you will have to reason through this yourself when the time comes for independent stuff. But for now, we'll use that as our reference. All right, last one up comes from they also plan to sell at least 10 shirts. So shirts is our Y and at least 10. So we set up our 10. At means we want the equal to. And then same thing, if 10 is the least, then I need to sell 10 or more. So we're going to have an X plus Y is less than or equal to 200. X is greater than or equal to 30, and Y is greater than or equal to 10. So for our graph descriptions, let's kind of think about what these inequalities are going to look like. Are they horizontal? Are they vertical? Are they diagonal? How will I need to graph these? So for that, X plus Y is less than or equal to 200. Because it has both variables, then this is going to be a diagonal. And so we're going to need to find our two intercepts to graph that diagonal. I need to know my x-intercept, and then I need to know my y-intercept. So we're going to use that same intercept rule to calculate those. So let's go ahead and calculate that. So I'm going to do it up there in the middle. So I'm going to do an x plus y equals 200 temporarily. And let's go ahead and solve for our x, which means our y will 0. And so when we solve for x is going to be 200. And then our y would be when x is 0, and then we would solve for y. And so same on this one, our y is 200 because of those coefficients being a 1. All right, so let's go ahead and graph our x-intercept at 200, our y-intercept at 200, and then it was a less than or equal to, so the equal to means it's going to be solid, and then we will be shading below for that less than piece. All right, for our next one, that is a Vux, which means it's going to be vertical. And I want the vertical to be when x is 30. And it is an equal to, so I am going to do a solid vertical at x is 30. And that is a greater than or equal to, so shading to the right to get larger. Our last one is a hoi, which means it is a horizontal. And our horizontal has to start at y is 10. It is an equal to, so it is going to be solid. And then it is a greater than, so we're going to shade upwards. So our final shaded region or our feasible region is going to be where those three colors mix. So on this one, it's going to be that inner triangle to the best that you can shade in, of course, without covering up too much information. All right, so this is pretty much where we stopped at the last time. So here's our last layer. The end goal of this question is if the HSB, the Hanes Sports Booster Club, sells hoodies for $25 and shirts for $15, what combination of hoodies and shirts need to be sold to maximize their profit? So to get that, what we're going to do is look for the vertices of our shaded region boundaries. And I'm going to mark those in a different color just to kind of stand them out. I'll just do them in black where these are intersecting at. Okay, so those are going to be those possibilities for our combinations because inside this shaded region, I have an unlimited amount of possibilities, right? I could have this point right here where I have 40 hoodies and 20 shirts, or I can have 50 hoodies and 30 shirts, or I can have 55 and all these different possibilities, right? Everything in here, every part in here is a different combination. But there's only certain ones that are actually going to provide the maximum. And then that comes from the very ends that we call the vertices. So because we have a triangle, we have three that we're going to test. So I'm just going to just take a note of what those ordered pairs are. No particular order, so I'm just going to work from my way bottom up and to the right. So it looks like I have a point at 3010. I have a point at 30 and 170. And then far right, what is that? 190 and 10. So if the HSB sells hoodies for $25 and shirts for $15, we need to write a setup with that information that we're going to use as our profit equation. So just writing that with our variables included, right? We said hoodies were X and shirts were Y. So our profit equation is going to be $25 for every hoodie and $15 for every shirt. We're going to use that as our setup and to help us with actually calculating for our profit. So we call those profit extremes, those very ends, those vertices. And all we're going to do is use substitution. And we're going to take each of those ordered pairs and we're going to plug it in and see what the profit would be for each one of those. And then that's going to help us determine the final maximum that we're actually going to want. So the setup for all of these is using that 25x plus 15y, but we're going to set up for substitution. So we're going to remove the x, and we're going to remove the y, and we're going to plug them in. So our first vertex, at least the one on our list, was 30 and 10. So we're going to type that in. to our calculators. Let's see. Looks like mine kind of froze. There we go. All right, let's do 25 times 30 hoodies plus 15 times 10 shirts. And we have $900 for one of our profit extremes. Okay, we're going to take that same profit equation, but this time with a different x and a different y. And so the second vertex that we selected was 30 and 170. So let's do 25 times 30 plus 15 times 170. And that would get us a profit of 3,300. Okay, and our last one, again, using that same profit equation, but with our last one, our last vertex, which was at 190 and 10. So we're going to type that in and see how much money we would make with that possible combination. And so that is 4,900. So from there, we're going to compare and see which one is the actual true maximum profit. And so with those donations, the best combination is going to be this one right here. It has the most money. So let's finish this thought out. To maximize a profit of, so the most money that we could possibly make is $4,900. The HSB, the Hays Sports Booster, would need to sell and then you're going to say how much was actually chosen. So that one used the 190.10. So that would be 190 hoodies and 10 shirts.